Thank you.
So, hello everybody and welcome to Rico's Defense. Let me just say a couple words. It's been an absolute pleasure watching Rico grow in confidence and in mastery over the years. And it's been a great pleasure talking to him as well because we have very opposite instincts about how to approach math sometimes. So I really have to apologize for all the times where you wanted an answer, I think, in terms of commutator identities, and I drew a little skit on the little picture on the board. Yeah, so.
Okay. So hello everyone. Thank you for coming to my talk today. Thank you to my committee for also serving to be here and support my research today. Okay, so today my talk is going to be on separating subgroups of odd Fn using homological representation. Okay, so here just we're going to give like a little outline. So we're first going to do a little introduction to introduce sort of the objects cared about in this talk. And then, yeah, you might need to find a seat. Yeah, we're still a little early.
Yeah, you're starting early.
Yeah, sorry, Dr. Darwin, we're a little early. No, yeah, but we didn't get there too much. All right, so for the introduction, yeah, we're just going to introduce some definitions to introduce the problem. Then we're going to give the approach to the problem, and we're going to explicitly show the idea for a specific case in this filtration that we're going to talk about throughout this talk, and see how it sort of generalizes to later terms in the filtration that we'll talk about a little bit later. And in this problem, we developed techniques to sort of do the same idea, but for different sort of subgroups of odd Fn. Okay, so maybe let's start off with what is odd Fn, right? It's in the title, so maybe we should define it. So odd Fn, it's the free group on n generators. It's pretty much the group with no non-trivial relations, right? The only idea, the relations or identities that we have is pretty much the relation given to us just by inverses, right? Usually we associate it to the fundamental group of the wedge of n circles, usually in topology. But nonetheless, it's some group, so we could look at its group of automorphisms, right? So we just look at odd Fn, this is our group of automorphisms, and there are bijective homomorphisms, right? They are structure-preserving maps that are bijective. So maybe just like a little example, you could always define a homomorphism on a finitely generated set by how it sends to the generators. And we just create one where maybe A2 and A1 swap with each other, and we sort of append on two A1s and an A2 to A3. Right, so this is just some automorphism of F3. Okay, so the next thing to introduce is a homological representation. So in homological representations, this is the idea. We're looking at subgroups of Fn where in fact automorphisms of Fn also lift to automorphisms of K. Right, so this is what it means to be characteristic by definition. So we get that odd Fn is a subgroup of odd K, right? And further, what we want K to be is we want K to be finite indexed. Right, we want it to be finite index for the two following reasons when we look at our homological representation. One reason is it guarantees that the rank of homology, which we're going to be acting on, is in fact a finite index or a finite rank Z module. This is just because covers act nicely with Euler characteristic in the index of the cover. So since we sort of know the homology of Fn is finite, we sort of know the homology of K is finite by how it sort of works with multiplicativeness of the index of the cover. And usually throughout this talk, we're going to be looking at homologies of subgroups, and the way we'll look at it is we'll see these homologies of subgroups really as the abelianization of this subgroup, right? Because this is really how homology is defined. And for throughout this talk, you could sort of see K as a cover of the wedge of n circles that's also a finite index characteristic cover. So there's a nice correspondence of that if you want to keep that in mind in terms of topology. Okay, so now we introduce what is a homological representation. So we consider these sort of maps that we could define from above. You could sort of inject odd Fn into odd K, and we could sort of see the natural map of odd K going into the automorphisms of the abelianization of K. And in fact, these automorphisms are the invertible matrices or the invertible maps on this free abelian group. So we call a homomorphism of the form gross of K, where it's equal to this composition of these types of homomorphisms. We call them homological representation, right? So you could see it just takes an element of odd Fn and then sees how it acts on the homology of K, right? So you could sort of see this of taking an automorphism of Fn and seeing how it acts on the homology of its cover K. All right. So now we'll talk about what the question that we're going to answer, right? So the question that we're going to answer is given two sort of nested subgroups, H and G in Fn. When can we sort of tell the difference of H and G in some homological representation, right? We know that H is a subgroup of G. Is there a way to sort of see G but tell the difference between G and H in this homological representation? And what makes it sort of hard, first of all, is odd Fn is not a linear group, so there's no sort of homomorphism that injects into like some bigger GLM space. So we can't just use sort of images and kernels to sort of get this image in subgroups really nicely. So what we're going to do in this talk is we're going to show that we could see this difference in successive terms in something we call the Johnson filtration. Right, so we're going to show that we can answer this question for a specific class of groups. And we're going to show once you could do this for a specific class of groups, maybe this extends to separating maybe more intermediate steps in between in the Johnson filtration. Okay, so before we sort of define the Johnson filtration, this Johnson homomorphism and stuff, we're going to need to define the lower central series. Okay, so we could define the lower central series as such. Let's let G be a group, and we define its lower central series where we let G1 equaling G, and we could then inductively define the next term by taking the commutator with the base group. Right, so we have sort of that structure, and what's sort of nice is when you take the commutator of the mth term and the kth term, you get something in the m plus kth term. So there's this nice sort of grading system with a multiplication with a bracket, sort of like a degree sort of preserving thing, but you could get larger than m plus k. But at least you know you have a bound. So some, I guess, properties we get of this lower central series is that if this eventually does stabilize to the identity, that's when we call G nilpotent. But the big thing that we're going to need, and we're going to look at usually in our Johnson filtration and our Johnson homomorphism, is successive terms in the lower central series, right? And their quotients. The idea of them, if we sort of look at GK modded out by GK plus 1, what is it saying? It's saying you're looking at GK, but you're inducing the relation up here that everything is going to commute with GK. So you could sort of see this by looking, and it's counting sort of specific deck transformations of a specific basis type. Right? You're really looking at deck transformations of a specific homology class, but that be infinite dimensional. But that's really what we're doing when we look at GK modded out by GK plus 1. And yeah, so when we look at this, when G is finitely generated, which we have, it's going to be this finitely generated free Rico abelian group. All right, so here's just a little example. So as we said, we could then look at G2 over G3. We're going to see later on that it's going to be generated by these sort of commutators, AI, AJ. So what that means, if it's generated by these commutators, what it means to be in G3 is that there's a zero number of these commutators, right? So maybe let's just see this. Let's consider this element in G3, in G2 mod G3, and see why it would add a zero number of maybe A2, A3 commutators, right? So maybe if we just write out this commutator element, this is what it looks like. When you induce the identity that everything commutes with an element of G2, which this in fact is, you can sort of swap them and you get something zero. So that's really what these successive quotients in the free abelian group are doing. It's counting sort of deck transformations in this infinite dimensional space of these sort of commutators that act like a basis. So from here, let's define the Johnson filtration. So the first step in the Johnson filtration we define, or the first group in the Johnson filtration we define as I, and or J1, and it's seen as the kernel of the automorphisms that go from the automorphisms to the automorphisms mod G2. In other words, these are the automorphisms that act trivially on the homology of Fn. Right? Since we said the homology of a group is that group modded out by its commutator, this right here represents the automorphisms on the homology of Fn. So this kernel represents which automorphisms act trivially on the homology of Fn. So this gives us some exact sequence. This exact sequence is given as such, and it shows us that on Fn modded out by I is in fact GLNZ, where this is GL of H1 of Fn. So what we could do is we could further extend this idea, right? We could extend this idea to now sort of toggling on the G index. We could extend this idea by looking at the kth Torelli subgroup, where we look at the kernel now of the map going from odd Fn into, into odd of Fn mod Gk plus 1. Okay. Sorry. So when we further define these groups, we get a filtration, similarly to how we did for the lower central series, but a little different. But so we get this filtration where at every step we could see it as the following set. You could see it as the elements in odd Fn, such that when you pass them through Gi plus 1, it acts like the identity, right? So what this means is you give me an element of the ith term in the Johnson filtration, and you give me an x in Fn. This means it's the identity, but you have to pay with some term in Gi plus 1, right? But the upside is we know for all x in Fn, we'll know that x inverse of f of x is going to give us something in Gi plus 1, right? So the idea is you give me an element of Fn, I'll give you an element of Gi plus 1. That's really what this tells us. And we could really look at this idea and sort of like abelianize it in the sense, right? You take an abelian group of G1, you take the abelian group or abelian quotient of Gi plus 1, and you look at this action. You look at this action and it creates a homomorphism called the ith Johnson homomorphism, where it lifts it as such. It now sees elements of the ith Johnson group, and then it associates it to a homomorphism that takes elements in the homology to elements of Gi plus 1's quotient, some quotient, right? And what's nice is this is now a homomorphism from an abelian group to an abelian group. Both are finitely generated, so we could really just see these as just rectangular matrices over addition. So yeah, this is some finitely generated Z module, some finitely generated Z module. Look at homomorphisms between them. They're just rectangular matrices over addition. And what does it do? It looks at the action that we just talked about. It takes an element of the ith Johnson group or the ith Torelli group. And then sees how it maps an element of homology by looking at x inverse f of x mod Gi plus 2. Right? And yeah, what it does is it sort of keeps track really of how elements of homology send to elements, of GI plus 1, and we're going to have a basis for these GI plus 1s mod GI plus 2s, so we have a nice sort of way to sort of count them. And what's sort of nice is the kernel of tau I is the next stage in the Johnson filtration, right? So what it means to be in the next stage of the Johnson filtration is that when it sends an element of, when it sort of looks at this action on an element of homology, it always sends it to an element of GI plus 2, right? That's what it means to be in the current. Okay, so maybe let's just see just in action really quick. Let's just consider F and J2. That'll map A1 to this element in G3 and times this element in G3, and this is how it works. Right, we're gonna look at tau 2F of A1. This looks like A1 inverse F of A1. It kills the A1, and then we get this now vector in G3 modded out by G4. Right, and what it does, it's collecting these sort of types of commutators, right? And we see there's this sort of bilinear sort of action on the powers of the generators, right? You got a 2, the 2 is able to come out of the bracket. You have a 4 here, 4 is able to come out of the bracket. So there's a nice sort of bilinearity with the commutators in this group G3 mod G4. All right, so now we'll look at the problem. So the problem is, does there exist a homological representation, rho k, such that you could tell the difference of successive terms in the Johnson filtration? So work from Dr. Hidari has shown that given Ji, when you look far enough down in the Johnson filtration, there will be a homological representation that could tell the difference, right? And further, he was able to show that when you pass these quotients of Ji modded out by Ji plus 1 through these homological representations, they also will be finite, right? And this is sort of surprising because the index of this quotient is infinite. So what this talk does is it sort of expands on this idea, and it does just a little better. It says that you could definitely tell the difference at successive terms instead of just looking far enough down in the lower central series, or in the Johnson filtration. Okay, so, and again, what we're going to do is use the techniques showed to solve this problem to further separate other intermediate subgroups in the Johnson filtration, or between the Johnson filtration. All right, so let's talk about the approach. So the approach is, what we're going to try to do is capture the information that the Johnson homomorphism captures in some cohomology class of some cover mod p squared, right? Because what the Johnson homomorphism did is it was able to count these specific sort of commutators. What we want to do is we want to see these commutators in some cover of some of out of 3 or out of n. Okay, so we're going to do this. Does the same thing. Yeah, we're going to show that there's going to be an element in Ji, but not in Ji plus 1, a cover K, and a cohomology class, such that for some x in homology, the action of the Johnson homomorphism is going to read off 0 through elements in Ji, but not Ji plus 1. But we're going to show that we can capture this action in the Johnson homomorphism, and this will be able to show that everything in Ji plus 1 is going to read 0 through the cohomology class. Okay. Okay, so again, the last slide said is what we needed was a cover, a cohomology class, and sort of a nice choice of F in Ji, but not in Ji plus 1. So what we're going to do is we are going to create a cover that's going to, we'll give in J, we're going to create a cover that's going to contain the jth term in the lower central series, and it's also going to need to be finite index, right? So that was sort of the next step that we needed to do, is construct this sort of cover. And what we're going to do is we're going to construct these subgroups using the jth term in the lower central series and sort of p powers for some positive integer. And this is going to guarantee that we are finite indexing characters. Okay, next is what we're going to do is we're going to have a cohomology class. So what is a cohomology class? Over a ring R. So all this is really a homomorphism from H1 of K with some coefficients in R, and it's going to map into the base ring. So it's a homomorphism that just maps linearly into the base ring. And again, what we said we wanted to do for this cohomology class was to read off some element in the ith Torelli group, but not in the I+1 Torelli group, such that it reads off something non-zero for that element, but for everything else in Ji+1 it'll read off 0. And really what it's going to do is we're going to be able to read a specific basis element in Gi+1 modded out by Gi+2. And we're going to read that through this projection map here. Okay. All right, so now explicitly we're going to do this. We're going to do this for the first Torelli group from the second Torelli group. So in this portion, we're gonna separate the first stage using the method that I came up with. Okay, so let's just recall taking the first Johnson homomorphism. What it is it takes an element of Torelli, sees how it acts on an element of homology by looking at x inverse f of x mod G3. So we're going to construct our cover. The cover that we're going to look at in question is this kernel of Fn into H1 Fn z mod Pz for some p, right? So the nice thing that we have here is that we can see it's sort of finite index because this is a finite index group, or this is a finite group here on the right. So by first ISO, we should get that it's a finite index cover. And we know that it contains all of G2 because we're mapping into an abelian group. So whenever you map into an abelian group, we know that the commutator, you have to pass through the commutator. So yeah, this is the cover that we're going to sort of look at. And we're going to see, let's just recall in G2 over G3, the sort of elements that we want to sort of count are these sort of Aij squares, right? And we want to count the number of Aij squares in some homology, in homology of some cover. But we're going to see that this sort of poses a problem. Yeah, so this sort of poses a problem, and it sort of looks like here as such. So for example, maybe let's take K to equal the kernel of Fn into H1 of Fn with Z3 coefficients. So we can see this as a cover, maybe we'll do this for F3. We can see this as a cover of F3, and somewhere along in F3, where this is maybe A1, A2, A3, we'll have this sort of grid. Right? Where maybe going this way is A2, 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 and going this way is A3, A3, right? So what we'd want to do here is we now see A2, A3 in homology. We see A2, A3 in homology because it's going here, 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 and here, right? That's a homology element. And so the idea is what we want to do is we want to be able to count 1, 1, 1, 1, 1, 1, 1, 1, 1 here for every deck transformation in the cover, right? But then we run into a problem. We run into a problem because this element here, if you count 1 on this element here, this is the same thing as counting 1 on the same element. If we add these homology classes together, this is the same thing as counting the element A2 to the third, comma A3 to the third, right? And that's something that has to read off 0 because this is 0 in homology. Because it's in the commutator of K comma K, this would have to read off 0 in H1 of K. So to make the cohomology class that we would want to do it over Z would be not well defined because you'd have something that would be 0 would have to read off P. or p squared. So the way that we sort of bypass this is do this idea mod p squared, right? Because what we'd want is 3 squared to equal 0. So this is the problem, and this is sort of how we patch that problem. So since the bracket sort of works bilinearly, when you look at the image of k comma k, we could sort of see that everything is going to arise with a p squared of some commutator of a type that we want to read. So the idea is to kill off all these things in the commutator intersected with G2. So yeah, so what we're going to do is we're going to do all these with coefficients in z mod p squared for some p, just so we keep a well-definedness sort of sake in our definitions. So really, how does this go in constructing our cohomology class? We really have the two following maps, right? We look at how G2 goes into K, because G2 is contained in K, and then see its image in homology, right? And then we have this other map that really reads off basis elements of G2 mod G3 mod P squared. And since what we just showed is that the image of K comma K with G2, its image in G2 mod G3 is going to be in P squared of that sort of free abelian group. So what's nice is now we could create this map here since the kernel of this map is contained in the kernel of this map. So what we've done now is we've captured all the information of the first Johnson homomorphism in the homology of this code using this cohomology class. So what we're going to do, let's just fix the A2, A3 sort of basis element, and we have the following. What's sort of nice in our construction of psi is we've included that everything in G3 has to be in the kernel by really this part here in our projection map. So since G3 is our kernel, what's nice about that is when passing this through sort of the action of the Johnson homomorphism, we get something in G3. And since psi contains G3 is in the kernel of psi, we get that this is going to read off something 0 when we look at this action for elements of J2. And then now what we need to do is just pick the map that's nice in I but not in J2. And the one we're going to choose is this following map. We'll send A1 to A1, A2, A3. And we have this computation. We have this computation through the Johnson homomorphism. And all we wanted to do is just create this nice computation to where this looks like a product of an element in G2 times an element of G3. So it's just a nice organization process when you pass this through the cohomology class. And when you do this, when you pass this through the cohomology class, you could use the homomorphism properties to nicely do the computation. And again, since G3 was in the kernel of psi, this will read off 0, and we do this p times, so this reads off p. So we've constructed an f such that it reads off something non-zero through this action through row sub k, and we've captured this in homology. And this is how we've separated the first Torelli group from the second Torelli group. Right, so we've shown that they have different images based on sort of how they act on this homology element. So since they act differently, we have definitely shown that they're not subset, or they're not contained in one another. Okay? And from here, we would just have to, we just extend this idea. Wait, do I still have time?
150.
What time is it now?
158.
158?
Oh, I'm way over then.
Yeah, take 2 minutes.
Okay, so yeah, okay, so pretty much this extends pretty much the same way for ji over ji plus 1. Sorry about that, I should have kept a running clock. But yeah, this practically does extend the same way. this extends the same way. You have the same sort of commuting diagrams and the same sort of containment of p squared. So that's why we have to do all of these separations mod p squared. And
You have 20 minutes though. You started at 1:30.
Oh.
Yeah.
Oh.
Yeah, I thought you had like
Oh.
50
No,
minutes.
you have 20 minutes
Yeah.
still.
Okay,
Oh, yeah.
cool.
Oh, yeah, go back.
Okay, sorry about that.
We're all like,
Yeah, sorry about that. I thought I got a little scared too. Okay, we're okay then. Sorry about that.
I wanted to see like this and said, no, don't do that.
Okay, sorry. I got scared there.
Sorry, I forgot that it was 1:30 as well.
Yeah, me too, honestly. I thought it was one. Okay, cool. So yeah, we can extend this now to later terms in the Johnson filtration. Okay, let's just recall maybe the ith Johnson homomorphism. What does it do? It or the ith Johnson ith Johnson group. What it looks at is it looks at the kernel of the map of automorphisms of Fn, and then you pass it through Gi plus 1, and it looks at this kernel. And what it does is we get this homomorphism, tau sub I, where it reads off how it sends elements of homology to elements of Gi plus 1, to Gi plus 1. It sees it in some abelian group. And again, what we're going to do is we're just going to capture this again in some homology of some kind. So again, we're just going to choose the cover as such. It's going to be generated again by pth powers and the I plus 1th term in the lower central series. Okay, and this definition, by the way it's generated, it guarantees that we are a characteristic finite index subgroup. The reason that it's finite index is because Fn mod KIP is nilpotent. It's nilpotent because it has the whole I plus 1 term in the lower central series, and every element is finite ordered. So these two things being true, you could sort of use the lower central series to show that you have finite index, right? But the important part of our choice of cover is that the image of Ji plus 1 intersected with this commutator is also going to be in p squared of this free abelian group. Right, and this again comes from showing these with bilinearity terms with the commutator bracket and stuff like that. It all comes from that idea. So from here we could now construct our cohomology class in the same way, right? We could map Gi plus 1 into our cover, and then look at how its image looks in the homology of that cover, right? That has some kernel, and that kernel being Gi plus 1 intersected with this subgroup. And since Gi plus 1 intersected with this commutator is contained in p squared of Gi plus 1 modded out by Gi plus 2, we could again create this map going this way. And it respects sort of the same image that the Johnson homomorphism shows. It shows the same image through these elements of homology as the same thing it would show in this, what it would show for the Johnson homomorphism. Okay, and the choice of F is definitely going to be sort of the same, right? So what's nice is now what we've shown now is for any I, we could always see the same information of the Johnson homomorphism, but it has to be done mod m squared. We can't do it over z, but we could do it mod m squared. So these cohomology classes in the Johnson homomorphism, they capture the same thing now. Or we found a way to make them capture the same thing. So what we're going to do then is now we're going to construct our nice choice of map. It's going to be pretty much the same idea. You'll have F in the ith Torelli group. That's going to send A1 to A1 times some basis element in Gi plus 1 modded out by Ga plus 2. And then it's going to fix everything else. And then we pretty much go through the same computation. We're looking at this action of F on A1 to the P. This is the same thing as looking at the image of the Johnson homomorphism. And then you run it through psi, and you then get again that and its image through psi is p, and something non-zero mod p squared. And by construction again of how we constructed psi, we have that gi plus 2 is always in the kernel. So since gi plus 2 is always in the kernel of psi, sorry, that's supposed to be psi, we know that psi of this rho kg minus I, a1 to the p, always reads off as 0, right? So again, so what we've done is we've done the following. We've shown that for all I, there exists f in ji and a cover k, along with a mod p squared cohomology class, such that for some element in that homology, that element f will read off something non-zero, but everything in J1 will read off something 0. So we've seen the difference in homology of some cover. Okay? And using the same techniques as what we did here, is we were able to later separate every element from Ji plus 1. So we could then see that what we end up showing is that the image of f through some homological representation is going to read off something non-zero through the cohomology class, but everything in Ji plus 1 will read off 0 in that same cohomology class. Okay. And yeah, so lastly, we said how we were able to look at further subgroups. We saw how we were able to separate further subgroups, and before we do that, we have to just define these two lattices in Gi modded out by Gi plus 2, and it sort of generalizes sort of what we did at the end of the day, kind of. So we'll have LA for some A as a subgroup of Ji, and we'll fix X as some element in the homology of Fn. Yeah, so LA is pretty much going to be the collective images through homology of tau I of A for all these functions A. Right, so this is just some subgroup of Gi plus 1 mod Gi plus 2, and this is just the lattice of the images through the Johnson homomorphism. Right? And we also have this lattice called LA of X, where this is tau I A of X, and we look at all of these images for all A and A. Right? We know this is a group here just because of the Johnson homomorphism in general. Okay. So lastly, here is the last theorem that we show, is if we have B is a subgroup of A is a subgroup of the I-Torelli group for some I greater than 0, then if either in these lattices we could see the difference in these lattices, we show that there exists a homological representation such that rho k of B is strictly contained in rho k of A. So the reason that we're able to do this is because we found a cover and a cohomology class that captures all of the information of the Johnson homomorphism. So if LB and L, so if these lattices sort of tell us about how these subgroups sort of map into Gi plus 1 modded out by Gi plus 2, we're able to capture all that information using the cohomology classes. So if you have a difference in these lattices, we can now tell the difference using the cohomology class, right? Because what we did in this talk is we showed that this lattice of Ji plus 1 was a 0 lattice because it always spit out something 0, but there was some elements in Ji that was able to spit out something non-zero. So we could also see this phenomenon in other sort of covers. Right? We could sort of see this phenomenon since we have the information of like the basis elements of Ji plus 1 modded out by Ji plus 2. So yeah, we could always find these sort of covers, mod m squared, so we have to do it in some sort of finite index cover, and we're able to see this difference. Okay? All right, so future directions. So I think just the next idea that we wanted to think about was, does there exist homological representations that separate B from A when they sort of have a different image in JI modded out by JI plus 1. That was something I think we were gonna look at, or maybe already showed, but yeah, that wasn't really fully fleshed out yet. And I think the big idea that Dr. Hidari wanted to look at was separating the derived filtration. So it's defined where maybe you take the first group to be Fn, and then you take successive commutator brackets of them. And the next idea is, given I greater than 0, does there exist a homological representation that could tell the difference of these groups, maybe? Okay. And yeah, that's pretty much everything that we looked at in I guess for the talk and this dissertation. Yeah, does anybody have any questions?
Any questions for Rico?
Rico, can you go back a slide?
Yep.
You don't have your chance.
Oh, sorry.
No, just kidding.
I was going to ask about you in this last question. One with the derived filtration.
Yeah.
What new challenges come up in this case as opposed to the ones you were looking at? Right. What makes this one harder? So.
I think when I think of maybe what makes it a little bit harder is maybe finding finite index covers that can maybe encapture all of these sort of things. Because what was sort of nice about the lower central series is you're able to sort of fit in all of the lower central series and then put in sort of Pth powers in with that group, and then that'll create this finite index maybe cover. So that's actually a big thing that we needed, and I don't know if we're gonna necessarily have that for these sort of things. Because when you start looking maybe at modding this out by this, you start getting like infinite dimensional homologies and stuff like that, and then that's a lot harder to look at in some local spot, I guess. Yeah.
For the definition of how you construct the homology class,
Mm-hmm.
there's a map phi. I missed the definition of how that came up.
Yeah. So this phi, we could just see how it naturally goes into the quotient of GI plus 2, and then tensor it up after.
Okay.
Yeah. So yeah, it would be the natural map and then like a tensor map after. And we could do that because these are free abelian groups.
Yeah.
All right, so let's thank Rico again. And we'll have to do people who are not on the committee leave it.